All right, so today we are going to talk about a local regularity theorem for mean curvature flow, as we promised. And we talk about some consequences or applications of this local regularity. So originally this is called the Brachis regularity, but we won't be able to talk about the full generalized version of it. This is a weaker version of it, but it already works for a large class of Brachii flows. So let's first recall a notion that we introduced in the previous lecture, the Gaussian density. First recall. So this calibrated M denotes the space-time track of the flow. And you consider some space-time point on the flow, on the space-time track of the flow. And the Gaussian density was defined to be this integral to the power n over 2. So exactly the same Gaussian density that appear in Huysken's monotonicity formula. You are integrating with respect to the induced measure on the hypersurfaces. Right. So this space-time track of the flow and each time slice is sigma t. So the calibrated M denotes the whole space-time track. You view it as a space-time manifold. And this is the Gaussian density. We introduced a few lectures ago. And if you recall that well, by definition, this is by the Huysken's monotonicity formula. So it has to, this is upper semi-continuous functional. So you might have space-time points with Gaussian density converging to it, to the space-time, to the Gaussian density at a particular space-time point, but it might jump up in the limit. Okay. And this local regularity theorem is talking about when the Gaussian density is very, very close to 1. Okay. So theorem. This is local regularity. And it's a weaker version of Brachi's regularity. And this is due to Bryan-White. Okay, so it says that for any dimension, there exists a dimensional constant that only depends on dimension n. So there is this dimension constant small enough, and you have a constant Cn also depend only on n. And m is the space-time track of a smooth mean curvature flow. So here we are only talking about smooth mean curvature flow here. And I will explain this. So this is, we want to talk about the regularity for the weak notion, the Brachii flow. So here we stay in the smooth flows, and then we apply it to the limit Brachii flow that is smooth, limits of smooth flows. Okay. So I'll explain this later after stating the theorem. Smooth mean curvature flow in a space-time neighborhood such that the Gaussian density is less than 1 plus epsilon n. When it's close enough to 1 for any space-time point x in U, and r is less than the distance of the point xt to the boundary of this space-time neighborhood. Then the second fundamental form at the point x at any point x naught t naught has bound a less than, this is the constant that only depends on dimension and is independent of the flow. Okay, distance. So this is also the, not the Euclidean distance, it's the parabolic distance. So where this p denotes the parabolic distance, where you consider the two space-time points, x1, t1, and x2, t2. This is equal to the distance between these 2 points are the maximum of these two. In the space, it's just the same Euclidean space distance. And in the time, you take square root. Okay. Right. So there's a dimensional constant bound that when the Gaussian density is close enough to 1, this smooth flow has a uniform curvature bound. And uniform curvature bound is a measurement of regularity. So recall that if you have uniform curvature bound, you can pass to the limit and preserve that to curvature bound give you C1 alpha, which is C2, which give you convergence in any C1 alpha. And then regularity can imply to higher standard parabolic regularity can improve the C1 alpha regularity to smoothness. So this curvature bound is really a measurement of regularity. Okay. Any questions? So let me make some remarks. All right, so the first remark is that this is a kind of regularity theorem called the epsilon regularity theorem. So similar epsilon regularity. Epsilon is the epsilon that is in the condition saying that the density is close to 1. Appear in many other geometric problems, like for example, minimal surface, harmonic map, and its heat flows, all have this kind of epsilon regularity when you have density very close to 1. Okay. And actually, this local regularity for the mean curvature flow is a parabolic version of the epsilon regularity for minimal surface. Okay. And the second remark that I want to make is here we are using Gaussian density. But this is not the only way that you can formulate this. So it can also be formulated using Euclidean density. So this density is really saying that in an integral sense, measure theoretic sense, it's very close to the Euclidean flat space. Euclidean area ratio. The Hn measure of T naught you intersect with X naught of radius R, and then dividing by the volume of the area of the Euclidean M ball. Well, when it is flat, this is equal to 1, but you can formulate this theorem also using this Euclidean volume when it's also very close to 1. So these two notions are somewhat equivalent. This is appearing as one of the exercise problem in the problem set. So this Gaussian integral and the Euclidean area ratio, they actually can control each other. So you can use the Gaussian integral to control the Euclidean area too. So see exercises. Okay, and the third remark I want to make is that so as we already mentioned, this is a weaker version of Brachi's regularity. So the full general Brachii regularity tells you that it doesn't require the flow to be smooth flow. It tells you that you have a measured theoretic Brachii flow, and if this density, Gaussian density, is close enough to 1, or the Euclidean density is close enough to 1, then this measured theoretic thing is automatically smooth, and it has this curvature bound. So that's the full Brachii regularity. However, this weaker version works for Brachii flows constructed via elliptic regularization. In the last lecture. So last lecture, we proved the existence of a Brachii flow starting from a closed embedded hypersurface via the elliptic regularization procedure. And because there are limits of smooth flows, so for each one in the sequence that is approximating the limit flow, each one in the sequence is smooth. So it satisfies this curvature bound. And this curvature bound can pass to the limit. And you have a C1 alpha regularity for the limit, which improves to the C infinity regularity. Okay. So as long as you are smooth, a limit of smooth flows, this works. And it also works for first time singularities. So when you consider tangent flows at first time singularities, so before that time it's all smooth. So you do a blowing up and zoom in, you get the tangent flow. So the convergence to the tangent flow, if the tangent flow is smooth, then this convergence has to be smooth too. because in the previous time the flows are already smooth. Okay. So first time singularity works. So before we get to the proof of this theorem, so let's mention some consequences first. Any questions up to now? So first is a corollary. So that's already mentioned in the remark. So if the Brachii flow is a limit of smooth flows such that this Brachii flow calibrated in such that the Gaussian density at the point is less than the same 1 plus epsilon, then there exists an R. So this is there exists an R such that the flow is smooth in R neighborhood of x naught t naught. So why does it fit into the theorem? So recall that you have the upper semi-continuity of the Gaussian density, right? So if this guy, if this Brachii flow has Gaussian density already less than 1 plus epsilon n at this particular space-time point, then you can find a small neighborhood, small enough R, such that all the Gaussian density centered at nearby points are also bounded by this 1 plus epsilon. And then the conditions in the local regularity works. So it requires that the Gaussian density has to be small in a small neighborhood around that point. Right? So this can be seen through the upper semi-continuity of the Gaussian density. Okay. So the second corollary is the gap theorem. For self-Schinkers in Rn plus 1. So we already know that the Gaussian density of the flat plane with multiplicity 1 as a self-Schinker has Gaussian density equal to 1. And the gap theorem tells you that there is a gap, epsilon n, that between this Gaussian density 1 and 1 plus epsilon n, there's no other self-Schinkers. Only self-Schinkers. Actually, this is more general. So this gap theorem works for any ancient flows, not just self-Schinkers. Is a flat plane. Up to rotations, of course, you can rotate the flat plane. It's still a self-Schinker and it's still Gaussian density equal to 1. So let's give a proof of this using the local regularity? Suppose not. There is this some point, say x naught, x -1 in the time -1 slice of a self-shrinking flow, such that at this point, the second fundamental form is not vanishing, so it's non-flat. Then we know that by self-similarity shrinking, so a self-shrinker evolves under mean curvature flow by self-similar shrinking, we call that. And every slice are rescalings of the -1 slice. So xt equal to is in the t slice of the flow. And by scaling, you have at this point xt, the second fundamental form is having a norm. When you rescale it, the second fundamental form rescale correspondingly. And this is non-zero. So when you let t go to 0, this is going to infinity. So it's blowing up as t approach 0 from the left. And recall that we have this criteria for singularities. So if the second fundamental form blows up, it has to be a singular point. And this is a contradiction to the local regularity theorem, that if it is Gaussian density below 1 plus epsilon, it cannot be a singular point. And this is actually a first time singularity. So you're considering a smooth embedded self-shrinker. And the first time singularity that you occur is at time 0. So before that is all rescaling, and at time 0 you have a singularity because the second fundamental form blows up. Okay, any questions? All right, a third corollary is the convergence to the tangent flows. So this is the corollary of the full brachial regularities. You don't actually need to restrict it to the first singular time. So, but the version here we are stating is working up to the first singular time, but the full brachial regularity works for all later times. So if x naught, t naught is in a brachial flow, and a tangent flow at x naught, t naught is a smooth embedded self-shrinker with multiplicity 1. Then, so recall that the tangent flow is obtained by parabolically rescaling around that point. So the convergence. So you have a sequence of parabolic rescaling, lambda I, around x naught, t naught. So originally you have a tangent flow in the measure theoretic sense. This convergence is in measure theoretic sense. But if the limit is actually smooth at multiplicity 1, then locally you will satisfy this almost unit density, because locally every smooth submanifold is Euclidean when you are restricting to a small enough neighborhood. Right. So so this convergence is actually C infinity. So this Brachii regularity theorem is really telling you that if you are close enough as measures to a smooth flow, then you're actually close enough as C infinity smoothly to a flow. Okay. All right. So these are some of the consequences of the local regularity theorem. So in the remaining, I'll give a proof of this local regularity theorem. So this is a proof that actually, so the ideal proof argument is called the blow-up argument. It's a proof by contradiction. And this method is a method that is very widely used in geometric analysis and partial differential equations. So proof of main theorem. So it's worth to take a look at it. So we actually prove something stronger, not just the second fundamental form bound. That's like a C2 bound. We actually prove that it has the C2 alpha bound. Okay. So to do that, we first need to introduce a C2 alpha norm, a geometric C2 alpha norm for hypersurfaces of flows. Okay. So definition. So for M, a space-time track of a flow, we define K2 alpha at x naught t naught. So you pick a space-time point, and we define such a geometric C2 alpha norm. So because hypersurfaces are graphical locally, and when you talk about C2 alpha norm, it has to be the graph of a function. So we introduce a local C2 alpha norm to be the infimum of lambda, such that the parabolic rescaling of this flow around the x naught t naught point. So you move the point you want to consider to the space-time 0 and parabolically rescale it. So because these are smooth flows, so the proof of the theorem only we only prove theorem the local regularity theorem for the smooth flows. And because it's smooth, it's locally Euclidean. When you scale it enough, when you scale lambda, when lambda go to infinity, it's going to converge to the flat space. So when you rescale it locally, the graphical norm is very close, is as close as it can be to zero, to the flat space. Okay. Intersecting with the ball B1 of size radius 1 times time interval from time -1 to 1 is the graph of a function u with u C2 alpha norm in this space-time neighborhood less than 1. So there is always such a lambda. So when you scale it enough, you are pressing the C2 alpha norm down and you are making it flatter and flatter. Okay. So where the graph of u is x1 up to xn, and then the xn plus 1 coordinate is the graphing function. And then you have a time coordinate. So this is in r n plus 1 cross r. In the neighborhood, in this neighborhood. So when you scale it enough, so this C2 alpha norm is defined to be the infimum of the scaling factor, such that after scale by this factor, the C2 alpha norm is 1. So it's a geometric notion of C2 alpha norm. So when it's already satisfying this C2 alpha norm bounded by 1, then you don't need to rescale it. So lambda is 1. So as you can see, the graphicality is really a very strong property in mean curvature flow. So you can, in some sense, view the graphicality as the curvature estimate. Right, so the curvature bound is in some sense telling you that in how large of a region that you are graphical. So this is, if you are in larger region that you are graphical, then you have smaller curvature. So the curvature is really some sort of the scale of graphicality, if you view it that way. Okay. So that's why we want to talk about everything in local graphical. It tells you a lot of things. So now we can get to our proof. Oh, before that, we have to also need to define also denote. So this is the K2 alpha norm with respect to a point. We can define a K2 alpha norm, a geometric C2 alpha norm. In the neighborhood. So this is also the same idea when you define the C2 alpha norm that is degenerating when you're approaching the boundary of a neighborhood. So this is the supremum of xt such that the distance of xt to the boundary of u times the K2 alpha. So it's the supremum of the product of this point to the boundary times the K2 alpha norm at that point. So it's degenerating at the boundary. Right, so we'll claim that the main theorem follows from the following claim. The conclusion under the same condition in the main theorem. This right. So I made a typo here with the notation. So I should put the U to here, to the subscript. Okay. The K2 alpha norm with respect to this U neighborhood. A uniform constant C. All right, so it follows from the claim because if you have a uniform bound on this K2 alpha norm, then you have a uniform bound on local C2 alpha norm already. And if you have such a C2 alpha norm, so because C2 alpha is compactly embedded in C2, so after passing to the limit, you will have the limit is also uniformly in C2. And if you are uniformly in C2, because uniform C2 bounds the second fundamental form, right? And the second fundamental form is what? The second fundamental form is the second derivative projected to the normal direction. So it's bounded by the second derivative, the full norm of the second derivative, right? Okay, any questions? Okay, so let's prove this claim. So it's a proof by contradiction. Suppose not. So by definition, we can find a sequence of counterexamples. Sequence of flows, counterexamples, which is Mi. In a sequence of neighborhood, you have to take a counterexample of sequence for every element in the conclusion. Such that the conclusion of the claim does not hold, which means that this K2 alpha U UI norm of the sequence of flows is equal to Si blowing up to infinity. So it does not have a uniform bound. And we will draw a conclusion out of this, draw a contradiction out of this, which means that the claim has to be true. Okay. Well, but also, right, so you have to satisfy the condition in the local regularity, the almost unit density conclusion, such that this conclusion of the claim does not hold. So, but you still have to satisfy the Gaussian density, Mi x t r is less than 1 plus epsilon I for all xt in Mi. So these are the conditions in the local regularity that it has to hold. So let me move this a little bit leftward. to the boundary of ui, and epsilon I go to 0. So you're supposing, so you want to prove there exists such an epsilon n gap. So suppose not, then there is a sequence of counterexample that with this density is actually converging to 1. So they are less than 1 plus, less than 1 plus epsilon I. So in the limit, the Gaussian density has to converge to 1. So now from this sequence of supposedly counterexamples, you can parabolically rescale this sequence and obtain a new sequence. So parabolic rescaling of a mean curvature flow is still a mean curvature flow. And translation. So you can always translate the point that you want to consider to the spacetime point 0. We can assume without loss of generality such that there exists an xi ti. So by the definition of this k to alpha norm, it's si. So there's this xi ti in mi such that, so this k to alpha norm in the neighborhood ui is the distance function. To the boundary ui of k to alpha norm of xi ti. So it's equal to, the supranorm is equal to si. So you can always find a point such that this product is greater than 1/2 of si. So by definition, the supranorm of all these xi's, ti's, which is also going to infinity. And without loss of generality, we can always assume that. So you can always parabolically rescale it and translate the xi ti to 0, such that xi ti and the k to alpha norm at xi ti is exactly 1. So you can always scale it so that it's scaled to 1. And only now the sequence, only the distance function are approaching infinity. So we will still label it to be the same mi. Is exactly equal to 1. Okay, so which means that this distance function xi ti. So after this rescaling, so we don't relabel it to be a new flow. So just consider it to be the same flow after rescaling and translation. But now the distance of this point you're considering to the boundary of the neighborhood is approaching infinity. This flow is in a larger and larger neighborhood. So in the limit, it's going to be defined on the whole space-time, Rn plus 1 times R. Okay. To the boundary is greater than, also converging to infinity, because we rescale the k to alpha to be 1 already. So now, for any fixed point, any arbitrary point, we want to deduce a uniform curvature bound for any on any compact subsets of space-time, so that we can extract converging subsequences. for any xt in Ni have So let me know if you have any questions or if I'm going too fast, okay? So by definition, this is the K2 alpha U norm, which has to be bounded by Si less than Si, which is 2 times Si over 2. And this guy is less than 2 times the distance of Xi Ti boundary Ui. So we already rescale it so that the Xi Ti's are 0. So we might as well just write it that way, right? So without loss of generality, we already suppose the Xi Ti are moved to space-time origin. And this is converging to infinity. So we might just write the space-time 0, 0 here. And thus, by triangle inequality, the K2 alpha norm at xt. So after you divide this distance function to the right-hand side, you obtain 2 times distance 0, 0 to ui. Xt to ui. So by triangle inequality, this is less than 2 times to ui minus the distance between. So let's move this a little bit. Sorry. Right. So the sum of this is triangle inequality. So the distance of 0, 0 to ui is bounded by the distance between 0, 0 to xt and xt to ui. Okay. All right. So this is equal to 2 times 1 minus xt. Right. So the distance between any fixed given point xt to the space-time origin, this is a fixed number. And we already, well, by our assumption, the distance from 0, 0 to boundary ui, this is bounded below by 1/2 of si, which is going to infinity. So the denominator is going to infinity. So in the limit, it's going to converge to 2. So which means that for large enough I, this is less than 3. Okay. So you have a uniform bound on any compact subset of space-time on the C2 alpha norm, the geometric C2 alpha norm of the sequence of flows, right? on any compact subset. So it only depends on the distance to the origin. So on any compact subset, this is bounded. And this geometric K2 alpha norm is a local C2 alpha norm. So when you pass to the limit, you obtain a, so this gives uniform local C2 alpha graphical norm. And so, but again, by the Arzela-Ascoli. So if you are uniformly in C2 alpha, then this is compactly supported in C2. So you can extract a converging subsequence which converge in C2. So the compactness theorem can tell you extract a subsequence so that the flows Mi converges on any compact subset to a limit flow M infinity. Right, so where does the contradiction come from? So you have limit flow, and recall that our contradiction assumption saying that the Gaussian density is less than 1 plus epsilon I. So the limit flow, when you pass the limit, the Gaussian density has to be exactly 1. Okay. The Gaussian density is always at least 1 if the flow is non-empty. And now it's bounded by, for any 1 plus epsilon, for any arbitrary epsilon small. So with Gaussian density equal to 1. So if you have Gaussian density equal to 1 at all scale, that means your monotonicity formula, Whisker monotonicity formula is equality, right? Because the Gaussian density when you take, so this M infinity T naught minus R square So the Huysken's monotonicity formula has to be equality because when R approaches 0 is 1 and it's at least 1 for all R large. So it has to be constant. And recall that Huysken monotonicity being constant means that this is a self-shrinker. So this limit flow is a self-shrinker. But however, this is for any arbitrary space-time point. So it's shrinking, it's a self-shrinker with respect to any point. So if it is actually shrinking, it cannot, because if it's shrinking to shrinker with respect to one point, it cannot be a shrinker with respect to other point. The only possibility is that is actually the flow is static, cannot be actually shrinking. So it's a minimal surface and self-shrinker and Gaussian density equal to 1. So it has to be a minimal cone with Gaussian density equal to 1. So the minimal surface has the corresponding rigidity theorem telling you that it can actually only be the flat plane. So this is the flow of the flat plane. static flat planes. So it's a self-shrinker, but cannot actually shrink. All right. So now where's the contradiction? Right. So by definition of this K2 alpha norm, so you have mi intersecting in a larger and larger. So by rescaling, it's in a larger and larger ball, a larger and larger neighborhood in space-time. Is the graph of ui, where, of course, the ui has to satisfy the graphical mean curvature flow equation. So recall that the graphical mean curvature flow equation is d dt ui minus Laplacian ui is negative. So I have to sum these up. Negative, you sum the i's, you sum the k and l. So I is already used. dku, dlu, dk, dlu. So we denote this right-hand side in homogeneous term to be fi. So you have the, by definition, ui converge to 0. So in the limit, it's a flat plane. So ui has to be 0. It's constant, but you can always translate the height so that it's 0. And this convergence is in C2 alpha because the C2 alpha norms of these u's are bounded by are uniformly bounded in C2 alpha. So the convergence is in actually C2 alpha. But however, now you can look at the right-hand side. So it only involves second order derivative. This is C2. And these are first order derivatives. Now, if ui is converging to 0 in C2 alpha, then we have that. So you only take up to 2 derivatives. So there's still alpha left. C0 alpha is converging to 0. And then you can apply the parabolic Schauder theory so to the linear operator. So apply parabolic Schauder. I'll state out what that is. For this operator. So this is a linear heat operator. So parabolic Schauder estimate tells you that this linear operator is a bounded operator from C2 alpha to C0 alpha. So ui C2 alpha is converging to 0. 2. So this is because L is a invertible operator from C2 alpha 2CC alpha. So this is this sheltered parabolic estimate are really about the solvability of a parabolic equation. So you have a inhomogeneous right-hand side. You can invert it to get a solution which has bounded norm in C2 alpha when the inhomogeneous term is small enough in C0 alpha norm, right? So this is what the parabolic estimate is. And this is the contradiction because recall that we have rescaled so that at the particular space-time origin, this norm is equal to 1. So it cannot go to 0. Because this is rescaled to be always 1. So when you consider the graphical C2 alpha norm, there is always at least a point with C2 alpha norm exactly equal to 1. So this whole thing cannot just go to 0. The contradiction for large enough I. So which concludes the proof. Right. So this is the, as we said, this is the so-called blow-up argument. So you suppose the corresponding estimate does not hold. You find a sequence of counterexample, and using some compactness theorem, you get a limit. And you either draw a conclusion about the rigidity of the limit, or you draw a conclusion for large enough terms in the sequence. But however, if you prove estimate using this contradiction argument, you don't really know what the sharp constants are. For example, this only tells you that there exists such a dimensional constant epsilon n. But you don't really know what the best constant is. Okay. And you can't see it really from the proof. So let me finish this local regularity theorem with a remark on that gap. Okay. So there's a gap. Conjecturally, the gap epsilon I is equal to the Gaussian density of round sphere minus 1. So conjecturally, the next self-shrinker or the next Gaussian density that singularity can occur is that you are having a spherical singularity. Below that threshold, everything has to be smooth, and there's no other self-shrinker exist except the flat plane. This is already known. For curve shortening flow, you already know that because we have a complete classification of curve shortening flow self-shrinkers, embedded ones, which can only be the round circle or the flat plane. So this is obviously true. But also in dimension in dimension 3, this is due to Bernstein and Wang. So we already know that in the surface flows case in R3, you have such a gap, and it's optimal, okay, because you already have an example of self-shrinker, which is the round sphere. Okay. But in higher dimension, it's still totally open. All right, any questions about what we have gone to up to now? Okay, so perhaps let's take a short break. And we will continue to apply this regularity, local regularity, to talk about some partial regularity of mean convex flows. So let me take a picture of the attendance. Any questions up to now? No? All right, so let's continue. So in the remaining, we won't be really getting into the proof, but I'll try to tell you what consequences of this local regularity theorem can tell you about the partial regularity of mean convex, mean curvature flows. So recall that we say a mean curvature flow is mean convex if the mean curvature is greater than 0. So and by maximum principle, this is preserved along the flow. So if you have an initial mean convex surface, it holds for all time. And recall that we have a classification of the singularity models that can appear as tangent flow for the mean convex flows. So since the mean convex is preserved, so when you take tangent flows, this tangent flow has to be mean convex too. And the classification theorem, we call the self-shrinkers, which appears as tangent flows, can only be square root of 2k can only be all these generalized cylinders. For, of course, for mean convex mean curvature flows in Rm plus 1. So they are hypersurfaces, so have to have the dimension add up to n. K plus n minus k equal to n. And the first thing that we want to say is important is these tangent flows can only appear with multiplicity 1. So in which case, then your local regularity theorem can apply. So multiplicity 1 of smooth limit, then you do have smooth convergence to the tangent flow. And this is a consequence of the following non-collapsing. Tangent flows will appear with multiplicity So this is a consequence of the following non-collapsing estimate. But we have to first define what this non-collapsing means, non-collapseness means. So there's actually various ways of showing the multiplicity 1 in the mean convex case. This is only one of the way, a quantitative way showing that high multiplicity cannot occur. And this is this non-collapsing estimate is something that non-collapsing is something that also appear in Ricci flow. It's a crucial part of Perelman's contribution to prove the non-collapseness in Ricci flow. So definition. We say M0 in an n plus 1 dimensional space. So n-dimensional hypersurface. So it has to be mean convex before you talk about non-collapseness. That divides Rm plus 1 into two regions, interior region and exterior region. Then M0 is said to be non-collapsed, alpha non-collapse. This is a quantitative non-collapseness. If for every x in M0, there exists Bose in the interior and in the exterior. So this is in E interior, and this is in exterior. We can find Bose in these two regions that are tangent to M0 at x, and radius of the Bose at least alpha divided by the mean curvature at this point. So it has to be mean convex for the denominator to make sense. So if you draw a picture of what this means, so non-collapseness, well, this is not actually mean convex. Let's redraw this. So for any point, you can find that two balls in both of the region that this hypersurface divide the ambient space into, and its tangent at these tangent at the point X, touching the hypersurface M0, and the radius R exterior, R interior. They are at least bounded by alpha when you rescale the mean curvature to be 1, then it's bounded by alpha. But for any mean curvature, you have to rescale correspondingly. And this gives you a quantitative way to rule out high multiplicity. If this non-collapseness is preserved under the flow, then you rule out the multiplicity more than 1 automatically. So this is a theorem due to Van Andrews. So if M0 is alpha non-collapsed, then the mean curvature flow T in, it might be singular or might be extinct after some time, starting from M0 is alpha non-collapsed for all T in 0T. Oops. Right, so this is also a maximum principle argument. So we won't be able to prove this here now. So so it's also, you have to find a suitable function whose positivity really means this non-collapseness. And you check that the condition for the parabolic maximum principle holds for that particular function. So if it is initially positive, preserve the positivity for all time. And positivity means mean convexity, means non-collapseness. So this function is quite complicated function. And to show that the maximum condition for maximum principle holds is it's a tricky process. Okay. And well, this rules out corollary tangent flow to mean convex MCF appears with multiplicity 1. So this is because all the singularity model that we listed here for mean convex, mean curvature flows, they're here. Generalized cylinders. So for each particular one, you have a mean curvature bound, which change to that, which give a lower bound on the size of the balls. So there's the upper bound for mean curvature, which change to a lower bound when you make it into the denominator. So there's the lower bound of the radius of the balls that you can fit in from the inside and the outside of the hypersurfaces. Okay. And say, for example, if you have a cylinder or something that appears with multiplicity 2, you have maybe some larger one. Because, well, the convergence, if they converge with multiplicity 2, so after rescaling, it's still multiplicity 2. So before rescaling, they're actually really coming together, but the mean curvature has an upper bound. So this radius force should have a lower bound. And this is going to be a contradiction to the preservation of non-collapseness, that you won't be able to fit in a large enough ball. If they appear with multiplicity higher than 1, then these sheets come together and the balls can't fit in anymore. Okay. Any questions? So they appear as multiplicity 1 of only these singularity models, SK. And also notice that what does local regularity theorem tells us? It tells us that Rn is not a singularity model. So if the tangent flow is a multiplicity 1 plane, then that is a regular point. So you can only have this by the local regularity. And you don't really have multiplicity 2 or 3 planes occurring. So if you have a plane that appear in high multiplicity, that can arise as a singular point. But if it is multiplicity 1, it cannot. And so I will also write down this very general stratification theorem. So this is stated in the mean curvature flow, but this is a more general stratification theorem that actually holds in many other settings too. Okay. Theorem. Of singular set. So this is due to Brian White. If M is the space-time track, the space-time track of a mean curvature flow in Rm plus 1 times R, then the singular set S is stratified. So it can be stratified for each K. It's a union of S1 up to Sn, Sk from 1 to n. Where Sk is those singular points such that any tangent flows at xt splits of at most RK factor. Right, so you can see these are singularity models. So this theorem is holding not just for mean convex mean curvature flow. This is holding for any mean curvature flow. And actually, if you formulate it correctly, this theorem, stratification theorem here, stated here, is working for any, where it has the same parallel statement in any geometric problem, in many other geometric problems. In harmonic maps, you can have this stratification. Also, but it's stated, formulated in a different way. So because in that setting, you are mapping. So you're talking about whether the tangent map splits. And in the minimal surface, you can talk about the same thing, whether the tangent cones, which are also singularity models, whether they split. So in the flow case, it's tangent flow, splits of a RK factor. Then the Hausdorff dimension of SK is at most K. So this is a parabolic Hausdorff dimension. So you use the parabolic distance to define this parabolic Hausdorff dimension. All right, so what does it tell you when you restrict it to the mean convex mean curvature flow case? So as a consequence, so by the local regularity theorem, the Rn cannot be a singular point anymore. So any singularity models tangent flows of the mean convex mean curvature flow splits off at most now n-1 factors of R, right? So which tells you that if mt, sorry, this is m equal to sigma t, space-time check, is a mean convex mean curvature flow or Brachy flow. You can pass through singularities. You can continue the flow after singularities, but you can also talk about the space, but the singularity theorem about the whole space-time track. Then the space-time, so this is Rn, Brachy flow in Rn plus 1 times R for n-dimensional rectifiable meshes. Space, then the space-time singular set S has parabolic Hausdorff dimension at most. So it's actually codimension 1. So parabolic Hausdorff dimension is the Hausdorff dimension with respect to the parabolic distance that we defined before. Defined with respect to the parabolic distance. So the distance between these 2 points, x1, t1, x2, t2. This is the maximum of All right, so let me conclude with a final remark. So this is actually stronger than what one might think because of the parabolic Hausdorff dimension. And this is actually sharp. So, so the first remark is this is actually sharp. So because you will be able to have examples that the singular set is codimension 1. So just think of, say you have a round circle that already appear in dimension 3. So round circle. And you take the epsilon neighborhood. So T epsilon is the points that X distance X to S1 is exactly equal to epsilon. So you make this as an initial data. So this is the rotational symmetric initial data. You run mean curvature flow. So these are 2-dimensional. So this is 2-dimensional objects manifold in R3. So you run mean curvature flow. What happened is that after some time, this whole like marriage ring surface is going to collapse to a round circle. So after some time, have singular set. The whole collapse to the whole S1. And this is, well, this is in dimension 2. So n-1 is 1. So this is sharp in terms of the Hausdorff dimension. And you see that for this flow, the there's only one singular time, and it's all restricted to a time slice. Right. So so by this parabolic Hausdorff dimension is actually stronger than Euclidean Hausdorff dimension because the square root of distance in time, which means that the time axis is actually counted as 2-dimension. So which means that a singular set cannot actually be spread in time. So this parabolic Hausdorff distance tells you that sigma t restricted to any t has singular set at most Euclidean Hausdorff. When you restrict it to any time slice, the Euclidean Hausdorff dimension is less than n-1, just like this sharp example shows here. And any connected n-1 dimensional component of the singular set in space-time has to lie entirely in the time slice. So because if you already have a singular connected component of a singular singular set, if it is not lying entirely in a space in a time slice, so it has to spread in the time direction, but the time direction actually counts 2 dimensions, so it will exceed this dimension. Has to lie entirely in one time slice.